need to breathe. But actually, oxygen only makes up about a fifth of the air that we breathe. It actually makes up 21%. Another 78% is nitrogen. So I promise this class isn't going to be math heavy, but 78 plus 21, that is 99% of all of the air that we breathe are just nitrogen and oxygen. Everything else, all of this here, these are called trace gases. And yet, they are still incredibly important. Of that 99, or of that remaining 1%, 0.9 of it is argon. So 99.9% is nitrogen, oxygen, and argon. And then neon, oh, hello, let me go back, 0.002%. So, yeah, really the bulk is nitrogen and oxygen. Everything else is pretty tiny, has very trace amounts, and yet is still very, very significant. Now, that being said, nitrogen and oxygen, those concentrations are fairly consistent around the world. Whether you are in San Jose, California, or Seoul, South Korea, the air you're breathing is roughly 78% nitrogen, 21% oxygen. Maybe very slightly, but not that much. Now, some other gases have more variation to them. Water vapor is a big one. If you've ever been to the East Coast in the summertime, East Coast of the United States, you probably notice that the air there is very, very humid, whereas the air here in California is a lot drier. That is because the amount of water vapor in the air can vary greatly from place to place and from time to time. Carbon dioxide. Carbon dioxide is considered well mixed once you get above the boundary layer of the atmosphere. But down here near the surface, if you're in a place with a lot of trees, you may have a little less carbon dioxide. If you're in the middle of a big city with lots of pollution, you may have a little bit more carbon dioxide. But the average concentration is just 0.04%. But Alicia, why would we care about that? Well, that's actually up about 40% from 150 years ago. About 150 years ago, this was actually 0.28%. 150 years ago. So that represents, I mean, doing the math, that represents about a 40% increase. Methane has also seen a pretty big increase, even though it has an even smaller concentration. These three variable gases, water vapor, carbon dioxide, and methane, actually all belong to a very important category of gases called greenhouse gases. And they play a very important role. But yeah, if you were to take a look at a recipe using a pie chart of our planet's atmosphere, this is approximately what you'd get. You would get 78% nitrogen, 21% oxygen, 1% everything else. And yet that 1% everything else is actually very important. Let's talk about those greenhouse gases. If you remember a few slides ago, I mentioned that the air is the atmosphere keeps our Earth warm. That's because of greenhouse gases. Now, before I continue on, let me ask you, how many of you have ever thought of greenhouse gases as a bad thing? Right? Guilty as charged. I've considered greenhouse gases bad before. I mean, if you watch so many infomercials and so many television shows, you'll hear things like, greenhouse gases are bad, greenhouse gases are evil, greenhouse gases should be murdered. actually, as a self-identified climate alarmist, I'm going to tell you right now, greenhouse gases are good. They are our misunderstood friend in so many ways. Here's why. Greenhouse gases are mostly transparent to sunlight, meaning they allow sunlight through them. However, our Earth gives off a different kind of heat called infrared radiation. Those greenhouse gases absorb that infrared radiation and radiate a part of it back down to the surface of the Earth. This keeps our planet warm. This is how every greenhouse in the world works. It lets sunlight in to heat the planet up, and it doesn't let heat escape, keeping the surface nice and warm. If, because of greenhouse gases, Earth's average temperature is approximately 15 degrees Celsius or 59 degrees Fahrenheit. That's the average global temperature of the Earth. If we were to take away all greenhouse gases, like tomorrow, like somehow we were to suck up all water vapor, all carbon dioxide, all methane, all nitrous oxide, all the other we get rid of all of them. Our Earth would be 59 degrees Fahrenheit colder. Now, let's do a crude example. Just humor me for a second. Look at your phone's weather app and look at what the current temperature outside is. Subtract 59 degrees from that. That would be, again, this temperature difference would not necessarily be distributed evenly across the world, and there's a lot of differences and stuff like that. But just for the sake of thinking, just to demonstrate this, imagine what it would be like right now if the temperature outside was 59 degrees cooler. Where I'm at today, the high temperature was 91. 91 minus 59 is 32. That is the freezing point. Yeah, that is the freezing point of water. Today I'm wearing a nice sundress. It is, it's very warm outside. I'm inside an air-conditioned office, trying to stay cool. If it was 32, I would be wearing very different clothes. I'd probably be wearing a jacket and boots, and I love those clothes, but imagine having to wear those in the middle of June. That would be the world without greenhouse gases. Humans wouldn't be able to survive. Here's why. We need certain temperatures in order to grow food, to raise livestock, in order to eat. Those significantly lower temperatures would not allow that to happen. So without greenhouse gases, our planet would be too cold to cultivate food. It would be too cold for us to live. Now, other organisms may still be able to cut it, but we wouldn't. Humans would die in this environment. So, yay, greenhouse gases! However, greenhouse gases, as good as they are, they have a dark side. You ever hear of too much of a good thing? That is what we're experiencing with greenhouse gases now. The more greenhouse gases we have, the warmer the Earth gets, because the more of a greenhouse effect we get. The more heat gets trapped in, the warmer Earth becomes. Our next door neighbor, Venus. Believe it or not, Venus actually absorbs less sunlight than Earth. Yeah, it actually absorbs less sunlight than Earth. But because its greenhouse effect is so strong, it's significantly hotter. It has an average temperature of 890 degrees Fahrenheit. Why? Because it has more greenhouse gases than Earth. So greenhouse gases are good, but like your favorite food, like sushi, or like coffee. I love coffee. Too much of a good thing makes it bad. In a world without greenhouse gases, we would be a lot colder because most of the energy that comes in would also be able to escape as infrared radiation. We'll actually talk more about how this works in the next module when we talk about radiation. So don't worry, we're going to get there. Um, but because we have greenhouse gases, sorry for my terrible drawings. This is why I wasn't an art major. Because we have greenhouse gases, a lot of that escaping heat gets absorbed and then radiated back down to the earth, keeping the earth warm. And so we have a nice balmy 59 degrees Fahrenheit. Now, that being said, there are some key greenhouse gases. Water vapor, believe it or not, is a potent greenhouse gas. Here's the deal with water vapor, though. Water vapor is very here today, gone tomorrow. Today could be very humid, tomorrow could be very dry. Water easily condenses out and rains back down to the surface of the earth. Water vapor is a potent greenhouse gas, but it is not a long-lived in the atmosphere greenhouse gas. The average residence time for a water vapor molecule is about 10 days. Ozone, believe it or not, ozone is also a greenhouse gas. We'll talk a little bit more about why ozone is so important in a moment. But here near the surface of the earth, ozone has greenhouse properties. But ozone down here near the surface of the earth is very unstable, meaning it doesn't hang out for long. It falls apart and decays into other things, molecular oxygen, as well as what is called nitrogen oxide and nitrogen dioxide. Connects with some of the nitrogen on our planet. You remember our air is like 78% nitrogen, so it connects with some of that. So it doesn't hang out here very long. Nitrous oxide, also very similar. It does not hang around for too long, and it has a very, very low concentration. Really, the two greenhouse gases we are most worried about are carbon dioxide and methane. And here's why. Carbon dioxide is by far the most concerning greenhouse gas. It is the one that has the biggest effect. Methane is number 2, but carbon dioxide is like the head honcho. Carbon dioxide occurs when you have things that are made up of carbon. So this can include coal, wood, sugar, carbohydrates, all these things that have some carbon in them. That carbon reacts with oxygen. That carbon reacts with oxygen to produce carbon dioxide. Now, don't show a chemist this formula. They will scream at me. Carbon is a diatomic element, so this equation wouldn't necessarily be like the most kosher. So don't tell a chemist that, don't show them this. But they're organic material, such as oil, petroleum, is mostly liquid carbon. Coal is mostly solid carbon. Those react with oxygen, and if you do something to catalyze the reaction, burning, that can catalyze the reaction, and all of a sudden, you get carbon dioxide. Well, here's one of the things about carbon. We found that carbon burns and oxidizes beautifully. And as such, because it burns and oxidizes beautifully, it creates a lot of carbon dioxide. And that burning releases a lot of energy. And we can use that energy to turn turbines. We can use that energy to move pistons up and down. We can use that energy to turn wheels. Suddenly, you can get from here to San Francisco what would have been a multi-day journey 300 years ago. You can get there now in 45 minutes because we've got good at burning fossil fuels. Because we got good at burning fossil fuels. Because of this, however, the amount of carbon dioxide in our atmosphere has risen significantly. In 1850, it was about 280 parts per million. Basically, what this is, if I were to take 1 million molecules of atmospheric air, throw them on the ground and count them out, 280 of them would be carbon dioxide. To today, and actually, this number is actually a little low. We're actually closer to 420 parts per million. I'll accept anything over 400. This is a high you do not want. This is a bad high. And yes, I know what I'm talking about. A gentleman named David Keeling in the late 1950s realized that this was getting concerning. And so he set up a carbon dioxide observation station on Mauna Loa in the late 1950s. And so over the past roughly 65 years, we have been monitoring changes in carbon dioxide at Mauna Loa. So this is actually, and this was from 2017, but if you were to actually look at the numbers now, we are actually closer, again, to about 420 parts per million. But the overall signature is the same. If you notice, there has just been a gradual, steady ramping up. Now, if you notice, though, I just drew like what looks like a smooth curve. But what we're actually seeing, I'll use a different color for this. What we're actually seeing is the zigzag pattern. Up, down, up, down, up, down, up, down, up, down, up, down. I like to call that Bart Simpson's hair. You ever watch The Simpsons? Bart Simpson has that spiky hair. Kind of looks like that. Take a moment, pause this video, and just take a guess. What do you think causes that? If you guessed seasons, you are correct. Why? Because here in the Northern Hemisphere, during the summer months, we have a lot of photosynthesis happening. Trees are awake, they're stretching out, they're spreading their leaves, they're photosynthesizing, and they're sucking in a lot of carbon. During the summer months, we'll use a different color here. During the summer months, carbon dioxide concentrations are going down. So summer. And then what happens as we get into September and October? Well, pumpkin spice latte comes out. I put back on my favorite pair of brown boots. And trees start to shed their leaves and go to sleep. Now, when they do that, they actually release carbon dioxide into the atmosphere. Why? Because they still need energy. They're not dead. They still need energy. So they consume the sugar that they have built over the last 6 months, and they release carbon dioxide, and that causes carbon dioxide concentrations to go up like so. Let's see if I can move it. Oh, yay, it's been good. That causes carbon dioxide concentrations to go up. Oops, like so. So if you ever hear some politician telling you, well, you know, carbon dioxide's been going down the last 3 months, seasonal cycle, that's why. But if you actually look at the big picture, there is a noticeable upward trend. Now, just for context, we do have ways of measuring carbon dioxide other than that Mauna Loa station. Ice cores, which we'll actually cover near the end of this course, do a really good job of doing that. And we have right here ice core data. And basically, prior to the Industrial Revolution, carbon dioxide concentrations were bopping around 280 parts per million. And then we started burning stuff. They started going up gradually, and then our population exploded. And whoop. Last gas I'll talk about for this lesson, ozone. Ozone, near the surface of the Earth, ozone behaves like a greenhouse gas. And it's actually a part of what's called photochemical smog. Down here near the surface of the Earth, ozone bad. However, higher in the atmosphere, ozone good. The reason why is because higher in the atmosphere, specifically in what's called the stratosphere, talk about that in a moment. In the stratosphere, ozone is actually very essential. And the reason why is because there are certain rays of sunlight called ultraviolet rays. If they made it to the surface of the Earth, they would cause mutations in our skin cells, which would increase cancer rates and basically plunge the average lifespan of a human being on Earth. That would be no bueno. We don't want that. So, ozone actually blocks, it absorbs those nasty UV rays from hitting the surface of the Earth. It absorbs them and keeps them up there. They don't reach the surface of the Earth, and hooray, we survive. Ozone forms naturally in the stratosphere. It forms naturally up there. The conditions, the lower atmospheric pressure, the different concentrations in gases, it's just easier to form up there. Over the past 150-ish years, we down here have had these gases called chlorofluorocarbons, CFCs. They have been considered miracle gases for us. Unfortunately, they wreak havoc with ozone. They're bad. We don't want that. So, when they have been released into the atmosphere, they break apart ozone and they actually cause a decline in ozone concentrations. Now, there's some good news. The good news is we have actually gotten CFCs under control and our ozone layer is healing. If it wasn't for that, though, all this nasty UVB radiation and actually UVC as well would be making its way down to the surface of the Earth and messing us up. Instead, we only have to deal with UVA radiation, which gives us bad sunburns. Still got to wear sunscreen, especially fair-skinned people like me. This actually became a big issue in the 1980s. In the 1970s and 80s, we noticed an increase in skin cancer cases, specifically in the Southern Hemisphere. And after launching a bunch of observation missions, we discovered that there was actually a significant decline in ozone concentrations, especially in the early spring months in the Southern Hemisphere over Antarctica. Why then and how? That's a little bit beyond the scope of what I can talk about now, but basically all the right conditions come together. It's really, really cold after months of darkness. Lots of chlorofluorocarbons have been able to build up. The colder air allows for chlorine atoms to break off. And then the moment sunlight comes, boom, those chlorine atoms wreak havoc on those oxygen, on those ozone molecules, breaking them apart. Again, that is 30,000 foot overview. I cover that a lot more significantly in my climate change class. So just a review, the atmosphere is the envelope of air that surrounds Earth. It's here because of gravity, so yay, gravity. The atmosphere is mostly nitrogen and a decent amount of oxygen, which is good. If we had larger amounts of oxygen, we would get boom. That would not be good. Greenhouse gases trap heat in, keeping Earth warm. Ozone is important in the upper atmosphere. Now, when I say upper atmosphere, what am I talking about? That's in the next video. So I will see you then.